Hello everyone, welcome back. Today we're going to talk about the Lagrange error again. So this is the second video that I'm making on Lagrange's error, and so we have two examples that I want to do for you guys today. Example 10 says let f be the function given by f of x equals cosine of 3x minus pi over 10, and let p of x be a fourth degree Taylor polynomial. So right now I know that n is equal to 4, right? Because it's a fourth degree Taylor polynomial. It's also telling us that about f at x equals 0. So the equation we're going to use, actually, we're going to make our center actually equal to 0, right? So c is actually equal to 0 here. It says use the Lagrange error bound to show that this f of 1/4 minus p of 1/4, this absolute value, is less than 1 over 500. So basically what this means is that this is the actual value of our function, and this is going to be the actual Taylor series approximation. Right, so this is actually going to be the Taylor series approximation. And so what this is just asking us is that when we find the error, we're going to know that the error is actually going to be less than 1 over 500. So that's really all this is saying. So the only other thing that I need to do is just say, well, what's our x in our equation, which we're going to get to in a second here? Well, it's just going to be 1/4, right? Because you can see in the problem we're actually evaluated at 1/4. So without further ado, what I want to do now is write the equation for what the Taylor error is. So it's going to be p of n of x, and it's going to be f of n plus 1z, and then the absolute value of x minus c to the n plus 1 all over n plus 1 factorial. And so you guys can see that before I even wrote the equation up, I already know what the x value is. We know that's 1/4. We know the c value is 0. And we know that n is equal to 4. So I can actually go ahead and start plugging things in before we even worry about what this guy is right here. So it's going to be, the denominator is going to be 5 factorial. And I know that x is going to be 1/4 minus 0 all raised to the 5th power. So the only thing that's a little bit tricky about this problem is figuring out what this value is here. So I talked about it in the video prior. This is the maximum value, our derivative, our n plus 1 derivative is going to be. So since we're looking at this, I want to know what the maximum value is going to be. I want to know what the maximum value we're going to get when we're looking at the 5th derivative of our function. Okay, so what is that? So let's actually look at the 5th derivative of this problem. So let's find this. Let's actually find what this value is. So the first thing we're going to do is we're going to find the first derivative. And so we're looking at our function right here. Our first derivative is going to be negative sine of 3x minus pi over 10. And then we're going to multiply by 3, right? We have to use the chain rule here. So our first derivative is going to be negative 3 sine of 3x minus pi over 10. And so our second derivative is going to be negative 3 cosine of 3x minus pi over 10 times another 3, right? So what we really have here is we just have negative 3 squared, right? Negative 3 squared and times cosine of 3x minus pi over 10. So if we find our third derivative, hopefully you guys will see that when I find this derivative, it's going to be negative 3 squared, and then the derivative of cosine is negative sine, so it's actually going to be 3 squared sine of 3x minus pi over 10 times another 3, right? And so you guys can see that this is equal to 3 cubed sine of 3x minus pi over 10. So to save a little bit of time here, the fourth derivative is going to be 3 to the 3rd times another 3, so 3 to the 4th. So the fifth derivative at some value z is going to be 3 to the 5th. So this value here, the maximum value of a fourth degree polynomial, is going to be the 5th derivative of the value, which is going to be 3 to the 5th. So this is actually going to be 3 to the 5th. And so that's how we're going to find this value right here. So 3 to the 5th. And then once we simplify this, we can actually get the value for our error. And using a calculator, we're going to get 0.0019. And So this is what we get for our error. And if we were to go back and find out what the value of 1 over 500 is, well, that's actually 0.0020. So we can now say that this right here is actually greater than the actual value that we found for the error. So we know that we are good. All right. Now, one other question that I tend to get when I'm doing this question is, well, what happened with the sign of 3x minus pi over 10? Or why didn't we care about the rest of this derivative? And what I tell students about this part, if you just look at the function sine or cosine, so no matter what derivative, if it's sine or cosine, the maximum that these will ever be is 1, right? We're looking at where c is equal to 0. So we're looking at the maximum 1. So we really are multiplying minus 1. And I should have mentioned that earlier because I know that that's a question I get every time when I do this problem with my students. So I just want to tell you that as well. So we really do have to take into account this rest of this function. But again, sine and cosine, no matter what we do, we plug in for this, the max value we're going to get for it's going to be 1. Alright guys, let's go ahead and do example number 11 now. It says let f be the function having derivatives for all orders of real numbers. The first 3 derivatives of f at x equals 2 is given in the table below. Our typo there was 4. The fourth derivative of f satisfies the inequality must be less than or equal to 50 for all x in the interval of 2 to 2.5. So it says use Lagrange error bound on this approximation to f of 2.1 to explain why f of 2.1 that we're going to get using the Lagrange error must be less than 8.5. So I did an example pretty similar to this in my previous video. It was actually example number 9. So all we're going to do here is we're going to find what our approximation for f of 2.1. And so what we're going to do here is we're going to actually find the Taylor approximation using this chart, and then we're going to add to it the error that we're going to get using the Lagrange error formula. So the first thing we're going to do is actually figure out what the Taylor series for this is going to be. So let's find what the Taylor approximation is. Before I do that, I just want to say very quickly, because we need this for both of our problems here, x is going to be equal to 2.1, right? This is the approximation I told you guys about when we do Lagrange. This is the approximation. It's given to us right here. And then the c, our center, is going to be equal to 2. And that's what that's given to right here. So when we're finding the Taylor approximation for this, we're going to do our first term. Well, our first term is just what f of 2 is, which is going to be 8. And then we're going to find the first derivative, which we have here is 4. And then remember, we're going to subtract our x minus c, right? So 2.1 minus 2 raised to the first power over 1 factorial. So this is our Taylor series. And then we're going to then find the second derivative, which is 16. And we're going to do now 2.1 minus 2 squared over 2 factorial. And so in my previous videos, I talked about like this is all about the 1s, and this is all about the 2s. And then we're going to do 18, and then again 2.1 minus 2 cubed all over 3 factorial. All right? And so once we put all this in our calculator and we get it, we're going to get a decimal answer. We're going to get 8.483. Right? So that's the first part of our problem. So now all we need to do is find the Lagrange error, and then we're going to add these two things up, and we better get less than 8.5. And you can see we're already really, really close here. But the Lagrange error is going to actually be pretty small. So we're going to be okay. Okay, so let's actually talk about the Lagrange error. So I'm going to write it up again, what it is. And so we're looking at this problem, and we have a degree of 3, right? So our n is actually equal to 3 because we're looking at the third derivative. So we're going to be n of 3 of x, and that's going to give us f of 4z, right? Remember, this is n to the n plus 1, and then it's going to be x minus c to the 4 all over 4 factorial. So this is my fourth example of this, so hopefully you guys know it's n plus 1, so I'm going to go ahead and just do that. And so let's go ahead and plug in what we know for this. And so we actually, in one of the previous examples, we were given this really awesome thing. We were told, oh wait, it's right here, right? So this is the maximum our fourth derivative can be. So we can go ahead and write down that this is going to be 50. we're going to go ahead and write down that x is 2.1 minus 2 raised to the 4th power, all over 4 factorial. And again, if we use our calculator, we get 2.083 times 10 to the negative 4. I'm going to add that to our approximation. And this is now less, this value right here is now less than 8.5. So we did exactly what we need to do. Alright guys, so I hope that these examples help you with Lagrange. Alright guys, I'll see you guys next video.